Welcome back to the lecture on automotive vision. Today we want to discuss the chapter about behavior recognition. The slides of this chapter have been created partly by Jonas Phil, a former PhD student at the Adam Opel AG. Here is a list of references for this chapter. We are dealing mainly with hidden Markov models, and therefore the main references are the textbooks on hidden Markov models and how to use them in various applications. So you might consider the book of Russell and Norvig about artificial intelligence. It contains a chapter on hidden Markov models, some German book, Mustererkennung mit Markov Modellen, a book for various application areas, which at least shows the basic algorithms in a nice way. Then a tutorial by Rabiner about hidden Markov models and how they can be used in speech recognition. And although we are not dealing with speech recognition here, all these methods can be used as well for behavior recognition of autonomous vehicles. The fourth and the fifth paper are papers which are more focusing on the topics of vehicle and traffic scenarios. These are papers that describe how hidden Markov models can be used for behavior recognition. Before we start to discuss these methods, let's have a look at some pictures which we've recorded with our experimental vehicle on some highway scenarios. And the question in all these pictures is, will a certain vehicle change its lane or will it stay on its lane? In the first image, this vehicle is always somehow marked with an orange circle. So in this case, it's the small passenger cars behind the lorry. And the question is, will this passenger car change the lane or won't it change the lane? Will it stay on its lane? So you all are somehow experienced with driving. Maybe you have a driving license yourself, but I'm sure you have joined others in driving on highways, and you might have an idea what this vehicle will do. There might be some arguments in such a situation that the vehicle overtakes, and there might be some arguments to say that it does not overtake. So you might make a guess. What happens in this situation? Will the vehicle overtake the lorry and change its lane before the ego vehicle arrives at the respective position, or will it stay on its lane and stay there at least until the ego vehicle has passed? So that's the initial situation. Now let's go some images further in the video sequence. Then the situation looks like that. Now again, you might guess, what will the vehicle do? And maybe on the first image you were guessing that the vehicle will change its lane, or that it's more likely to change its lane. Seeing this picture, maybe you might modify your expectation, and you might say that it's not that likely that the vehicle will change its lane, at least not in front of the ego vehicle. If we go one step further, the situation looks like that, and now it becomes apparent that it's very unlikely that the vehicle will overtake. It's not yet impossible, but it's unlikely. And of course, now we see what happened. The vehicle did not change its lane. It was following the lorry. Now let's have a look at a different situation. So again, we see a pedestrian car in front of us that is driving on our lane, and we want to guess whether this vehicle will do a lane change or won't do a lane change. So if you look carefully, you will find that in front of that vehicle there is also a lorry. Some points in time later, the situation looks like that. Well, we now can see that there is even another vehicle ahead of this vehicle that we are focusing on. And we can also see that somehow these two passenger cars are not on the same line again, but that the vehicle that we want to predict is somehow deviated already a little bit to the left. And now we see, now it becomes apparent that the vehicle changes its lane, so now it's actually doing a lane change, crossing the center line between the two lanes. And that's the result. The vehicle now is on the left lane. A third example, so here again we focus on this black vehicle on the right lane. Will it do a lane change? And here you might already say maybe it's unlikely because there's no reason for that vehicle to make a lane change. There is no obstacle or slow car ahead of it. If we follow this video, we see that this initial guess became true. So it didn't make a change. And a fourth example, again a situation where we focus on a vehicle, the metallic vehicle on the right lane, that is following a lorry ahead of it. So if you look at that situation, will it do a lane change or not? Well, hard to say. You might make a guess yourself. Some points in time later, it looks like that. And now it becomes apparent that the vehicle really is doing a lane change. Maybe that's a little bit unexpected. At least for me, when I look at the first picture, I must really say this is a little bit unexpected concerning the whole situation. So now we can discuss what are the features which make us able to predict that how a vehicle will behave in future. Of course, behavior recognition is very important if you want to drive autonomously. Each vehicle is interacting with other traffic participants, and therefore it is important to be able to predict what these traffic participants intend to do during the next seconds. And therefore we need behavior recognition. Behavior recognition is based on the combination of techniques. First, we need different features from the sensor data. So features, pieces of information that we can extract, for instance, from video data. There are very many possible features, and we need several of them typically and need to combine them. Each feature itself might be ambiguous. So we might see something, but this alone does not allow us to predict what happens, because still there are several things that might happen. So only the combination of the features might lead to a clear guess what really happens. And of course, the chronological order is important in which these features occur. The same feature in different chronological orders might mean completely different activities. Let's make that clear on an example, namely the example of a lane change on a highway, as we have seen it on the pictures in the beginning of the chapter. There are many features. For instance, we might observe the indicator lights of the vehicle. They might be switched on or off, blinking left or right. We might consider the lateral position of the vehicle. Is it close to the center line of its lane, or is it approaching the boundary of the lane? The distance to the vehicle ahead might be relevant, as well as speed difference to the vehicle ahead and the speed difference to neighboring lanes. We might check whether there are gaps on the neighboring lanes, which are a prerequisite for a lane change, or whether there aren't gaps. And finally, we might also consider the speed difference to the assumed desired speed of the vehicle. Well, of course, we don't know the desired speed, but we can guess the desired speed, or at least from some features in the image we might get some ideas how the desired speed is. For instance, on a highway, by law, the speed of a lorry is limited to 80 km per hour, and therefore we can conclude that the lorry driver typically intends to drive with such a speed of round about 80 km per hour. If you observe a sports car, of course, we don't expect that the desired speed of the sports car driver is 80 km/h, but we guess that it is whatever, 130 or 150 or even more km/h. So there are features which allow us to at least make a rough guess of such a desired speed. The chronological order of a lane change can be described as a sequence of 4 stages. The first is we are following the ego lane, then we are preparing the lane change, activating the indicators, and maybe also already changing the velocity to adapt to the neighboring lane, then perform the lane change, and finally follow the new lane. Now 3 questions arise. How can we model the sequence of behavioral elements? How can we model the uncertainties of the observations and the ambiguities of the observations? And how can we use that modeling to draw conclusions and make guesses about the present behavior? There are several answers to this question from a scientific point of view. Here in the lecture we want to focus on hidden Markov models. Another alternative, which meanwhile has become also an alternative, would be deep learning methods, but in this case we stick to hidden Markov models. We already know what a hidden Markov model is. It is a discrete stochastic state transition system. Its observation and its successor state depend entirely on its present state and not on previous states nor observations. That was introduced in chapter number 5. The 2 formulas below state these independence assumptions that are expressed in the sentence above. If we want to use hidden Markov models for behavior recognition, we model the behavior of a vehicle as a sequence of states. So each state refers to a certain activity of the vehicle. And the sequence that typically occurs is modeled by the state transition probabilities. That means those sequences of activities or of behavioral blocks that typically occur in a row have large transition probabilities, while those combinations or sequences that are very unlikely in practice have very small transition probabilities. Observations are described with the measurand variables that are introduced in hidden Markov models, and the observation model that describes which observation occurs with which probability in which situations models the relationship between states and the observations. To go on, let us discuss the case of a very simple driving scenario. We assume that we are driving on a highway with a single lane. So there is no lane change possible, but we can just follow the ego lane. Still, we might be able to distinguish 2 different states. One is that we are driving with our desired speed. That would be something that we call free driving. Free because no one is somehow putting restrictions on the velocity with which we are driving, apart maybe from the legal regulations. But there is no other traffic participant which somehow interacts with us and forces us to change our speed. And the second state would be that we are following the vehicle ahead. Let's name that the following state. That means a vehicle ahead is driving slower than our desired velocity, so it forces us to slow down and drive with the same speed as a vehicle ahead. We can model that as 2 states and draw a state transition plot, and in which each state becomes a box. Now we can connect these 2 boxes with arrows indicating which transitions are possible and which are impossible. In this case, the thickness of the arrows also indicates how likely the transitions are. So that means, for instance, it is much more likely to stay in the mode of free driving than it is to change it to the vehicle following behavior. Keep in mind that the hidden Markov model assumes that we have a fixed, discrete time schedule. That means each second or each 100 milliseconds a new point in time occurs, and we have to describe in which way the state changes from an earlier point in time to the next point in time. So what happens within 1 second, or what happens within 100 milliseconds. And of course, if we are considering the behavior at such a set of discrete points in time, it is most likely that the vehicle stays in its present mode. And therefore these reflexive arrows are so thick, because we want to express that the most likely transition is the transition to the same state at which we are currently in. We could also put some probabilities to the arrows, and at that point let us assume that we just use our driver's experience, our own expertise, to derive these numbers. So in this case, for instance, 5% for changing the driving mode and 95% for staying in the same state. Now let's talk about observations. We might consider, for instance, the distance to the vehicle ahead, and for instance we might discretize this observation, so not provide numbers in meters or something like that, but just say, okay, the distance is small, the distance is medium, or the distance is large. So we have three different observations, or three different outcomes that the measurement of distance to the vehicle ahead might have. And for each of these possible outcomes, we assign a probability. So for each pair of state and possible observation, we provide a probability. So for instance, in this case, we might argue if the vehicle follows a vehicle ahead, it is very likely that the distance to the vehicle ahead is small. So in this case 50%. Or we might express that in the free driving state, the probability that the distance is large to the vehicle ahead is also very large, say 70%, like that. Please be aware that the direction of the arrow indicates the way, which kind of conditional probability we need to model. Namely, the probability of a certain observation given a certain state. So we assume that we know the state, and now we have to tell the system how likely is it that in such a state the observation looks like that. Not vice versa. The other direction is something that we come to next and discuss how we can solve it. But to model the behavior, we always provide the probabilities, how likely is it to make a certain measurement or observation, if we know that we are in a certain state. We could also introduce a second observation, for instance the speed difference to the vehicle ahead, and in this case might also discretize this observation into three different cases, namely we might be slower, or drive at the same speed, or drive faster than the vehicle ahead. And again, we assign probabilities that tell us how likely is it that a vehicle is driving slower than the vehicle ahead if it is in a free driving mode, for instance. Once we model that, we can ask how can we make a prediction or a guess of what is the current state of a vehicle. We assume that we observe the vehicle for a while, that we made a sequence of observations, and based on the sequence of observations, we want to make a guess. What is the most probable state that the vehicle is in? The answer to that is we want to determine actually the probability of the current state, st, given the observations z1 to zt. So the past up to the present observation. Or we want to make a prediction. So we want to say what is the next state of the vehicle. And, well, we already answered these questions on the slides on chapter number 5. We already derived an algorithm that we can use to calculate these probabilities iteratively. Now let us have a look what is the outcome of this algorithm for some artificial sequence of observations. The hidden Markov model is shown at the left upper corner of the slide. I've reduced it to only a single observation in order to make the visualization a little bit easier. So we have just one observation, the distance, and this distance is changing over time. So you see some plot at the right bottom corner of the slide. The upper plot shows the observation, the value of the observation. That ranges between small, medium and large. The horizontal axis is a time axis, ranging from point in time 0 up to point in time 100. Below we find the plot that shows us the probability to be in a certain state at a certain point in time, considering the sequence of observations up to that point in time. The blue curve is a probability to be in the free driving state, and the red curve is the probability to be in the following state. As we can see, somehow if we are observing large distances, then of course the free driving state becomes more probable. If we observe small distances, then the vehicle following state becomes more probable. And we can also see that somehow individual deviations from what we expect, so if the observation somehow is a little bit different from what we expect, then the filter somehow corrects this kind of imprecision. So for instance, in the time interval between second 50 and the second 80, the vehicle observes small distances for most of the points in time, but in between sometimes it also observes medium-size distances, and still the probabilities of being in the vehicle following state are still large. That means this kind of filter can compensate some mistakes in the measurements and some imprecision in the measurements. Now let's extend this task to the case of a highway with 2 lanes. Here the situation of course becomes more complicated, because we cannot just follow the vehicle ahead and have a free driving mode, but we can also do lane changes. So let's talk about which states do we need, which state transitions, which observations, and which observation probabilities. The state must model whether the vehicle is driving on the left or the right lane, and whether it is free driving or whether it's following a vehicle ahead or changing its lane. And the state transition model needs to model the possibility to switch between free driving and following, and it also needs to model that a lane change is done in a typical order of activities. One case to model that is to come up with 8 different states. We have free driving on the left lane and free following on the left lane, as well we have following on the right lane and free driving on the right lane. Furthermore, we have lane changing states, and to be able to distinguish some preparation phase and some execution phase, I've split up these lane changes into 2 separate states, namely a lane change state, a lane change preparation state, and a lane change execution state. And of course these states exist for lane change from right to left, and they exist for lane change to left from right, so that we come up in total with 8 different states. Now we can put arrows on the diagram to show which of these transitions are possible and which are not possible. Of course, here we have a certain amount of freedom to model the situation. So the solution that is provided on the slide is one possible modeling, but there might be also other kind of modelings for this problem that might also be suitable. So here I took the transition model from the one-lane highway example and put it that for the free driving to following transitions on the left lane as well on the right lane. And then I added some transitions that start at the following or free driving states and go over the preparation state, lane change preparation states, to the lane change execution states, and then to the free driving or following states on the other lane. Mind that to add the reflexive errors again, because of course still the most likely transition is the reflexive transition from a state to itself. Otherwise you would force the vehicle to change the state all the time, which is very untypical in real traffic. We could put numbers on these transitions using our driver experience for the moment, and the possible probabilities might look like that. Furthermore, we have to think about possible observations. There are several ones which are relevant, like the lateral position, the indicators, the distance to the vehicle ahead, and some more. When we go through the list, we find that some of these observations are discrete, take on discrete values, like the indicators, and others take on real numbers. So the lateral position or the distance to the vehicle ahead typically is measured in something like meters or so. That means we have some real numbers. And these two cases have to be distinguished. So one case of discrete observation values, for those cases we have to provide probabilities, observation probabilities. And for the continuous values we have to provide probability densities functions to model the relationship between state and observation. Let's do that for some examples. For instance, in the highway driving scenario, the indicator lights are very much relevant to be able to distinguish lane changes from non-lane changes. And of course, if we are in a lane change state, it is much more likely that the indicator lights are switched on, as if we are in a non-lane change situation. So we could have three possible observations for the indicator lights. The indicator lights might be switched off, or they might be blinking left or blinking right. And for the 8 different states in our modeling, which are now color encoded, we have to provide some probabilities with which the respective observation occurs for the respective state. These observation probabilities are given in the diagram as bars. The height of the bars refers to the probability. So if, for instance, we are considering the right to left lane change execution state, the dark brown state, we see that for that kind of transition we model that in such a case the probability to blink left is large, the probability not to have the indicator lights on is not zero, but so it is small but different from zero, and the probability to blink right is somehow very small, so close to zero. Maybe not zero, but very close to zero. If you consider the free driving state on the left lane, the dark blue one, we see that we model that in such a case the probability that the indicators are on at the left side or at the right side are rather small, very close to zero, while the probability that they are switched off are very large. Like that, you could go on through all the states, and for each state think about how likely is it that in such a state the indicator lights are off, on at the left side or on at the right side. The lateral position of the vehicle is another feature that is very helpful. Let us model that as a continuous variable. And we say that we model the lateral position of the vehicle on the road. As we can see here, we might consider, well, first the question on which lane is the vehicle, and then at which position on the lane is the vehicle. And we model the observation probability by a probability density function, for instance a Gaussian. Let's again start and have a look at some examples. If you are in the following on the right lane behavior, in the following on the right lane state, the light green state, then we expect that the lateral position of the vehicle is somehow centered around the center line of the right lane. And that is not deviating very much over the boundaries of the lane. And therefore we would put a Gaussian at the with an expectation value at the center of the right lane and with a certain standard deviation, so that the probability to be outside of the right lane is very close to zero. If we consider the lane change execution step for the left to right lane change, this is the state that is encoded with dark violet color, then of course we expect that the vehicle is somehow over the boundary of the two lanes. That means that somehow the position is between the lanes. This can be modeled with a Gaussian that is centered around the middle line of the road, that is centered about the boundary at which the two lanes are touch each other. We might also use a larger standard deviation to express that in this phase of a lane change, the vehicle moves from left to right, so that means it somehow is not driving permanently over a certain lateral position, but there is a larger interval of values that are acceptable, that have to be expected. And like that we could go on and discuss this for each observation, for each state and each observation. A third example would be the time gap to the vehicle ahead, which somehow reflects the speed and the distance to the vehicle ahead. And we might say, okay, if we are in a following state, so following the right lane or following on the left lane, then we expect that this time gap is small, that it is somehow close to 1 second, and we might put Gaussian density functions in this diagram, so that are centered more or less around 1 second, or maybe a little bit less or a little bit more, and express that in these situations we expect small time gaps. While in the free driving states we expect large time gaps, which we can express by a Gaussian density that is centered over a larger amount of time gap seconds, like 3, and that has a larger standard deviation. And for the lane change situations, it's hard to give some measurements, because maybe it's not yet really clear on which lane the vehicle is and what to expect. If you want to express that we are perfectly unsure about what observation we might get, then we put a very large, a very wide Gaussian into the feature space to express that we are very unsure and that all the values are somehow possible. This is done here as well with these kind of very broad Gaussian densities with large standard deviation. Using this hidden Markov model, we can test how the filter algorithm performs for some sequence of observations. This is shown here for an example. At the bottom you see the sequence of observations. The x-axis is the time axis, so running from 0 seconds to 50 seconds. And the vertical axis shows the observations. The blue line shows the observation of the indicator lights, where a value of 1 means that the vehicle is blinking at the left, and a value of 2 means that the indicator lights are switched off. The green line shows the measurement of lateral position, where 0 is the position at which the two lanes touch each other. Positive values are positions at the right lane, and negative values are positions on the left lane. So in this case, we observe positions first on the right lane, and then from point in time 22, 23, somehow the lateral positions are changing, and then later on we observe negative positions, that means positions on the left lane. Then the plot at the top shows the state probabilities over time for each of the 8 different states. Remember that for visualization purposes we color encoded the states. So dark green, for instance, means the state of free driving on the right lane, and light green means the state of driving, following a vehicle ahead on the right lane, and so on. So the same color encoding that you found on the slides before. And the plot at in the middle shows the probability of the most likely state as a bar plot. What can we see? Well, we see a certain sequence of observations create a certain sequence of most likely states. So in the beginning we are the filtering approach is rather sure that the vehicle is driving freely on the right lane, then somehow it changes from free driving to following a vehicle ahead on the right lane. Then at a certain point the observations provide pieces of information and features that tell us that the vehicle starts to execute or starts to prepare for a lane change to the left. Then this lane change is performed, and then afterwards the vehicle is driving on the left lane. At the beginning of this phase on the left lane, the algorithm obviously is not yet sure whether the vehicle is driving freely or whether it's driving, whether it's following a vehicle on the left lane. But then after a while, it becomes more and more apparent that the vehicle is driving freely on the left lane. So we can see that this model makes sense, and that this kind of sequence yields a nice modeling of what the vehicle is. On this slide I've compared the state estimation with a hidden Markov model that we have seen on the slide before. That's shown on the left part of the slide, and a state estimation without a hidden Markov model, where I was using only the observation model to predict the states, and I was removing the transition model. That means I was just estimating the state from a single observation only. And we can see that still the algorithm is able to do some realistic or some state estimation that is not too bad, but we can also see that the probabilities of the most likely state are lower than in the case on the left hand side. That means the usage of the state transition probabilities helps a lot to stabilize the whole estimation process. Now we know how we can estimate the state of a hidden Markov model, and that this is very useful to detect which is the current behavior and intention of a vehicle or a traffic participant. However, not all the drivers drive in the same way. So we might be faced with defensive drivers or aggressive drivers, or we might even be faced with drivers that are driving in a very unpredictable way because they drank too much, for instance. So, and the way that we were dealing with the situation up to now was not distinguishing these different driver styles. Of course, if we would be able to make a guess which kind of driver we are faced with, and if we could specialize our hidden Markov models to each of these kind of driving styles, then we could even improve the performance of the behavior recognition. Let's take the case of a defensive driver. We could, of course, use the same basic modeling, the same hidden Markov model, and change some probabilities or probability distributions to express that the defensive or careful driver is performing a different driving style than others. For instance, we might argue that a careful driver keeps larger distances to the vehicle ahead. So for instance, we could shift the density functions with which we model the time gaps that we expect to observe a little bit to the right. And this expresses that such a kind of driver is more careful and therefore keeps larger time gaps to vehicles ahead. We might also change the probabilities of the state transition model. For instance, a careful or defensive driver tends to drive more on the right lane than on the left lane. And that means we could, for instance, reduce the probability to stay in the left driving in the states that model driving on the left lane, and increase the probability to make a lane change back to the right lane. Another case would be a very aggressive driver. Of course, here as well we could shift the observations and reduce the time gaps that we expect to find, and also increase the probabilities to drive on the left lane instead of driving on the right lane. We even could add additional states, for instance a tailgating state. For a driver that drives on the left lane with a very small time gap and somehow trying to force the vehicle ahead to leave the left lane. So for instance, that would be this is done in this case. So we added a ninth state, tailgating. We added considerable state transition probabilities, and also some observations. And for instance, for this tailgating, we would assume, for instance, that the vehicle has a certain probability to blink left on the left lane, or to drive very much left on the left lane, or to drive with a very small time gap. These kind of drivers unfortunately exist in reality, so it's not bad to have them modeled. Now we have modeled several driver types. Now, of course, we have to ask, how can we find out which driver, with which kind of driver we are faced? So we do not know that, of course, a priori. We have to guess that or predict it somehow from the observations that we get. The answer is that we consider some probabilities, which are sometimes called the evidences. That's a probability of making a certain sequence of observations given a certain hidden Markov model. So if we assume that we have two different hidden Markov models, one for the defensive driver and one for the aggressive driver, we might ask, how likely is it that a certain sequence of observations occurs under the hidden Markov model of the careful driver, and how likely is it that we observe this sequence if we are dealing with an aggressive driver. So these are the probabilities that we are considering. But how can we calculate them? So first we observe that we can calculate this evidence probability and first add the present state st to these probabilities. And to keep equality, of course, we have to add over all possible states of st. That's the marginalization rule indeed. Now we can create an incremental or recurrent rule to calculate these probabilities. First, we consider that this probability of ST and the whole sequence of observations given a certain hidden Markov model can be rewritten as the probability of observing ZT, the present observation, given the present state and the previous observations times the present state and all the previous observation given the hidden Markov model. That's just by the definition of conditional probabilities. Then we can make use of the properties that we're dealing with the hidden Markov model. We know that the probability to observe a certain observation under a certain state is independent on previous observations. So we can neglect those previous observations in the condition part of the probability. And in the second part of the equation, we can add another variable, namely the previous state st minus 1, and sum up over all possible values of st minus 1 to keep equality. That's again the marginalization rule. Then in the next row, what do? Well, we split up this probability of st minus 1 and all the observations up to point in time t minus 1 into a conditional probability and a marginal one. Namely the probability of st given st minus 1 and all the observations up to point in time t minus 1 times the probability of st minus 1 and all the observations up to point in time t minus 1 given the hidden Markov model. Now we can make use of the stochastic independence properties of the hidden Markov model again and simplify the probability, because we know that the transition from state st minus 1 to state st does not depend on previous observations. We can simplify this term and end up in a simple state transition probability. So now we are at the end of these sequences of transformations, and we see that the kind of probability that we calculate on the left-hand side of these equations is the same kind of probability that we find at the rightmost position at the bottom row. However, the only difference is that on the left-hand side of the equation, it's the kind of probability up to point in time t, while at the rightmost side, it's this kind of probability up to point in time t minus 1. So we get a kind of iteration rule with which we can incrementally build up this probability from point in time to the next point in time. The other two probabilities are just observation probabilities and state transition probabilities that we have modeled in our state transition chart. So here we can see that again. So this kind of probability that we want to calculate on the left-hand side up to point in time t can be written as a combination of an observation probability, some transition probabilities, and that same kind of probability that we want to calculate, but for the previous point in time. So if we start with an incremental guess of that kind of probability for point in time up to point in time 0, then we can execute, so to say, this formula, implement this formula in a program and execute it again and again. And in each cycle of this algorithm, we integrate another observation. And by doing that, we can calculate the whole process for a long sequence of observations. This algorithm has a name. It's called forward algorithm. We set the prior probabilities, and that means the probabilities of the initial state for all the hidden Markov models, and then we calculate P of st given zt up to z1 based on P of st minus 1 and zt minus 1 up to z1. And then we repeat that until we have considered all the observations for all points in time, and finally we can calculate the evidence terms based on the formula that we have calculated so far, by actually integrating out the present state. Here we see the performance of this algorithm to calculate the evidence for two models, the aggressive driver and the defensive driver model for highway driving. At the bottom we again see the observations. That's actually the same set of observations that we were considering on some slides before. And above we see the logarithm of the evidence for the two models of the defensive and the aggressive driver. It shows the logarithm because the evidence itself becomes very, very small, very close to zero, and on this graph it wouldn't be visible anymore. It would be just more or less equal to zero. But if we take the logarithm, it becomes clearer and we can clearly distinguish which model has a larger evidence. And we see in the beginning both models have more or less the same evidence, but then it becomes clear that we are dealing with a defensive driver more likely than with an aggressive driver. Let's change this scenario a little bit and change the observations. Here are some other observations. So the vehicle is all the time driving on the left lane. The time gaps become very small, and then on the left lane the indicator lights on the left are activated. And here we see the evidences of the two models. In the beginning, the defensive driver model seemed to be more promising than the aggressive driver model, but then when the time gap gets small, and especially when the indicator light is activated on the left lane, then it becomes very clear that we are dealing with an aggressive driver and not a defensive driver. These are some basic ways to use hidden Markov models for behavior recognition. But of course, these are not all the tasks that we can solve with hidden Markov models. One task that sometimes occurs is that we want to calculate the most plausible sequence of states. So we are not considering which is the most likely state at a certain point in time and then at the next point in time, but what is the sequence of states that is most probable. That means we are searching for the states S1 to St that are maximizing the probability of all the states given all the observations. There's one algorithm that solves the task. It somehow is related to the forward algorithm, but a little bit more complicated in calculation. It's called the Viterbi algorithm. So we don't introduce it here due to limited time that we have, but it's good to know that there is an algorithm, and if you need it, you can look it up in literature. Another question is, how do we set up the transition probabilities and the observation probabilities in our models? Up to now, we were arguing that we have some human expertise in driving, and therefore we can set some at least reasonable probabilities. However, this might not be optimal. And there is an algorithm that is doing this job for you. It's called a Baum-Welch algorithm. The Baum-Welch algorithm takes a lot of example sequences, and from these example sequences and a basic structure of the hidden Markov model, that means a structure that contains all the states and the possible transitions, it estimates the transition probabilities and the observation probabilities. However, it cannot be used to estimate those from scratch. So even for the Baum-Welch algorithm, we need some reasonable model as initialization of the algorithm. And then the Baum-Welch algorithm can somehow optimize the transition probabilities and the observation probabilities. Let us conclude this chapter with some slides from Jonas Föll, who used hidden Markov models in his PhD thesis to model the behavior of vehicles. So the goal was to recognize driving maneuvers for short sequences of video sequences. And here he was distinguishing 4 different kind of behaviors or 4 different maneuvers, namely overtaking a vehicle, flanking a vehicle, following a vehicle, and free driving. What is the difference between overtaking and flanking? Well, flanking is meant to be the behavior where a vehicle is already on the lane on which it can overtake another vehicle. It is already there, it stays there, and it passes another vehicle without any lane change. While overtaking in this wording means that a vehicle is doing a lane change in order to pass another vehicle. Yeah, the sources of information that were available in his work were a vehicle sensor system with some cameras, radar and LiDAR sensors. And he had some maps available which he could use to model the course of the lanes and so assign different vehicles to different lanes. The approach that he was using is that he was using one hidden Markov model for each of these maneuvers, and then he was calculating the evidence of each of these models, and based on the evidence he returned some probabilities which describe how probable a certain maneuver is in a certain situation. The observations that he took were more or less just some distances of the two vehicles, so lateral and longitudinal distance of the two vehicles, and the speed difference and the acceleration difference. Since he was able to use a radar, the speed difference directly came out from the radar sensor, and the acceleration difference was also some derived variable from this speed difference. So how did he implement that? Well, first of all, he needed to create a hidden Markov model, so one for each maneuver. So he provided manually created a structure for each hidden Markov model, and he was collecting a lot of example data, a lot of example sequences, and then he was using the Baum-Welch algorithm to optimize the transition observation probabilities of each hidden Markov model. Once he did that, he could use those trained models to predict the behavior of others. And that worked as follows. So in each situation, for each pair of vehicles that he observed, he was initializing each hidden Markov model for point in time 1. Then he made an observation or a set of observations. Based on that, he was using the forward algorithm and calculated one iteration of the forward algorithm. Based on that, he could go back again to the point above, increment the time by 1 point in time, and go on like that. So he was using the forward algorithm in an incremental manner, in an iterative manner. In parallel, he could also calculate the evidence of each hidden Markov model, so by integrating out the current state. So that was what he did, and based on that, of course, then he could check which is the most likely hidden Markov model in this case. So what is the most likely maneuver that is observed at the moment? This slide shows an example, so an example video that was recorded on some test area with 3 vehicles. The 2 vehicles that we can see in the video that are driving on this test area, and the 3rd vehicle is the ego vehicle equipped with a camera and the sensors that is observing these 2 vehicles. So now when I start the video, you will see on the left hand side the video that is used to extract the features, and on the right hand side you see a plot which shows the probability, or better to say the normalized evidences for the 3 maneuvers: overtaking, following and flanking. So let's start the video now. So at the beginning, the 2 vehicles are more or less following each other, therefore the evidences of the models following and flanking following and overtaking are large, while flanking probability is low. Now we see that one vehicle did a lane change, and now we are more in a flanking or overtaking situation, and after the lane change back, we can see that the overtaking behavior has survived, so to say. Its evidence is maximal, or its normalized evidence, better to say. And so we know that this behavior that we observed is very likely to be an overtaking maneuver. So now we can summarize the whole chapter. We did introduce hidden Markov models for behavioral modeling. The state is used to model an individual behavioral block of the vehicle. Then the state transitions describe in which order these behavioral blocks might follow each other. The observation model describes the measurements that we can make and describe which measurements occur in which situations. And yeah, since the hidden Markov model is a stochastic system, it is able to describe all the uncertainties in terms of probabilities. So that's a big advantage. And of course, we have seen some examples for how we can use these hidden Markov models to model the driving on highways. Then we have seen that with this kind of models, we can do the behavior recognition. That means there are algorithms to estimate the most probable state, and they are based on the classical prediction innovation step, and they were already introduced in chapter number 5. And beside that, we introduced a new algorithm, the forward algorithm, with which we can also calculate the evidence of different models, and by that compare different models, which of them explains the data in a best way. That's the end of our chapter number 8 on behavior recognition. I hope you found it interesting what you've heard, and maybe you are motivated to read more in the literature that is referenced in the chapter. Furthermore, this was the last chapter of the whole lecture, so I hope that the whole lecture was interesting for you and that you enjoyed the digital format of the lecture.